The discrete uniform distribution is a probability distribution that describes a collection of outcomes. The key characteristic of this distribution is that the probabilities assigned to each outcome are equal. One example of an activity that produces a uniformly distributed outcome would be winning a raffle. Imagine we have 20 people. Each person enters the raffle by writing their name on a numbered ticket 1 to 20. So here are the tickets. And here is where people sign their name. Once all the tickets have been signed, they are collected into a box. To decide the winner, a ticket needs to be picked at random from the box. This means that the probability of winning the raffle is the same for each person that entered the raffle. In this case, the probability of winning equals 1 over 20. The discrete uniform distribution is described by its probability mass function that I've given here. This says that the probability of an outcome x is equal to 1 over n, where n are the total number of outcomes. Here this is defined as a set of outcomes here, starting with A, ending in B in steps of 1. This is often known as the support of the distribution, as this is where the probability is non-zero. If an x not in the support is passed to the probability mass function, the probability is 0. On the left, I've plotted an example of the discrete uniform distribution. Here, starting at A equals to 1, ending at B equals to 10. So the total number of elements here is equal to 10 minus 1 plus 1, which equals 10, which means that the probability of any of the outcomes 1 to 10 is equal to 1 over 10. And that's shown on the y-axis here. Let's look at calculating the expected value of the discrete uniform distribution. To calculate the expected value of a discrete uniform random variable, we need the formula for the expected value of a discrete random variable. I've written this formula here. This formula says that the expected value is a sum over all possible outcomes, where each element of the sum is that outcome multiplied by the probability of that outcome. You can think of this as a weighted sum. Notice that if the probability is very small for some values, then the contribution of this outcome to the sum would also be very small. To get started, we need to apply this formula. So the first thing we need to do is choose the limits for this sum. Now we know for the discrete uniform distribution, x starts at A and ends at B. From the discrete uniform distribution, we know that the probability of x is constant for all x, and it's equal to 1 over n. This means we can bring it outside the front of the sum. Like so. What we need to calculate now is this sum of x from x equals a to x equals b. This can be achieved by applying the formula for the arithmetic series. That's written here. So putting this together, so inside the brackets we need the first term of the sum and the last term of the sum. That will be a and b. So the n's will cancel out here, and we'll be left with a plus b over 2. This is actually the midpoint of the interval that starts at a and ends in b. Next, we will look at how to sample values from a discrete uniform distribution with an example in R. To get started with sampling values from the discrete uniform distribution in R, first we need to set some parameters. So this is done in code block 1, where we set a equal to 1, b equal to 10. We can derive n from that, the total number of outcomes, which will also be equal to 10. We then have this variable outcomes that is a vector that contains the numbers 1 to 10. And this is what we will sample from. So that's on line 6. Given that we know the total number of outcomes, we can then calculate the probability for each outcome. And we do that on line 7, is equal to 1 over n. In the second code block is where we actually sample from the discrete uniform distribution. So the function sample in R takes a vector of the values to sample from. It takes a number size, which is how many times to sample from it. We also have to tell it if we want to sample with replacement or not. And in this case, we need to make sure that we sample with replacement, because we need to keep the number of outcomes the same each time we sample. And then there's this part here where we tell the function the probability of each outcome. And this is just a vector of length 10, where each element of the vector is 1 over n. So just for clarity here, show that outcomes is a vector that looks like this. On line 11, we just gather these samples into a data frame with a single column called x that is equal to samples. In the third code block, we count the occurrences of each outcome. So now that the samples have been gathered into a data frame, what we do here is we use the count function. This will count for each outcome the number of times it appeared in our sample of 1000, and then we divide by the total number of samples to estimate a probability. So for example, in our vector of 1000 draws outcomes, let's say the number 2 appeared 110 times. So this means that in the sample data frame, we count that 2 appeared 120 times. And then we estimate the probability of that outcome by dividing by the total number of samples, which would be 120 over 1000. This becomes clearer in the printout in section 4 here. So in the first column, X, these are the outcomes. The second column, N, the counts of each outcome. And then the final column, probability, is simply N divided by 1000. Now that we have sampled from the discrete uniform distribution and estimated the probabilities of each outcome, let's look at visualizing this data. The data from these samples can be visualized in a plot such as this, where on the x-axis we have the outcomes, and on the y-axis we have the estimated probability of that outcome. Here I've drawn a reference line at the true probability for each outcome that we know is equal to 0.1. From this plot, we can notice a flatness characteristic of the uniform distribution. Now, the estimated probability for each outcome is not exactly 0.1 because we only have a limited number of samples. So the more samples we take, the better the estimate will be. For example, instead of taking 1,000 samples as we did, if we took 100,000 samples, then we would expect the variability in each of these bars around the true value to be reduced. I've included a link in the video description that contains the code for sampling from the uniform distribution and visualizing it as I have in this video. Please take a look, and thanks for watching.